So my name is Omer. I'm from MIT. I'm going to talk about program obfuscation outside the black box. So this talk has two parts. The first part will be kind of a survey talk about obfuscation. It's based on my PhD thesis, so if you want to read more about this, then you're welcome to check it out. Depending on how much time we have and how much energy we have, we might end with that, or we might move on to the second part, where I'll show you a simple construction of obfuscation from start to finish, together with a security proof. And since we're not too many people, then please feel free to stop me anytime with questions. So so let's go ahead and get started. So obfuscated code is code that is intentionally made difficult for humans to understand. So this code can be written in any language. Here, for example, we have obfuscated C code, but you can also think about machine code or Boolean circuits, whatever you feel comfortable with. And even though this code is difficult for us to understand, still it's a perfectly valid code. You can compile it, execute it, and it does exactly the same thing as this more familiar program right here. It just prints out the string hello world. So at first glance, obfuscation seems like something completely counterproductive. Usually in software development, we talk about things like readability and good coding practices. And clearly, obfuscation is kind of the absolute opposite of this. But still, it's kind of a really fascinating notion. So one reason that you should be interested in program obfuscation is for pedagogical purposes. So this here is a perfect example for how you should not write code. Also, this program kind of highlights a lot of the subtle features of our programming language. So the first time that I saw this obfuscated program, I was an undergrad. I was taking a programming course in C. And it was during our finals. We got this program, and we had to explain exactly how it works character by character. So that was the last time that the professor was teaching this course. So another reason why you should care about obfuscation is that it's kind of fun. So it's fun to write obfuscated code. It's very creative. It's kind of like an art form. And it's also fun to read obfuscated code and try to guess what it does, like a puzzle. So let's see a few examples. So can someone try and guess what the following program does, if you haven't seen this before? So this program approximates the value of pi, and it does this by looking at its own surface area. What about this one? So this implements a flight simulator. So one really nice thing about these puzzles is that if you lose patience and you want to peek at the answer, then you can always do that. You can just execute this code on a computer and see what it does. So this idea of peeking at the answer brings us to kind of a very important observation that turned this notion of obfuscation from something that programmers do for fun into a booming industry, something that has many, many applications in practice. So the observation is that you don't have to give away the answer to your puzzle. You could also obfuscate programs that contain secrets. And now you can't learn these secrets by just executing the program. The only way to learn these secrets is really to look inside the code. So it turns out there are many reasons why programs should keep secrets. Let's just see a few examples. So proprietary algorithms say that you developed a new image processing algorithm. So you want this algorithm to run on many machines, but at the same time, you may not want anybody to know how this algorithm works. You can use obfuscation to protect authentication or licensing mechanisms in your software, or basically any piece of security-sensitive code. The idea here is that if nobody knows how these mechanisms work, they become much harder to attack. Digital rights management, or DRM, this is what we call obfuscated code that controls the way that we access copyrighted information, preventing us from making illegal use of it. Hidden features. You can use obfuscation to create software that contains hidden features that only certain authorized users can access. And finally, one of the more common applications of obfuscation is to create what we call polymorphic code. So here, the secret is just the code itself. You want to create code that is hard to recognize or hard to sign. And as you can imagine, this is something that we often see in the context of malicious software that wants to avoid detection.
So is this, in practice, are the two middle, second and third bullets, are they considered solved? Or so for, I mean, this is a the practical solution now is just to have an online component to everything?
So I think it's sometimes you don't want online component for sure.
When you don't, is it something that is there code that actually is not?
So I think it depends on your adversary in your application. So if your adversary is just a user that has a smartphone and just wants to use the application, then sure. But maybe if you want to protect something so that no government, such a government won't be able to reverse engineer and understand how it works, then it's obviously not solved. So
I mean, that's for number one, but for, I mean,
it could also be for number
is all the games were patched because they had somewhere if rights management true, then not true, then exit, and then someone would remove that piece of software,
right,
and put it on a floppy disk.
Right.
Is this something that's been solved in the last 20 years?
So again, it only depends how much who you're trying to protect against. If you're trying to protect against something that's sophisticated enough, then commercial solutions are not like foolproof.
So someone who wants to sell it from a stand in Hong Kong.
It just depends how many hours of like someone that can read machine code you're willing to spend on this. If you're willing to, it's not definitely not solved.
It's not like
no. It's everything we have in practice is just you can consider it delaying tactics. Okay, so there's a lot more to say about obfuscation in practice, but today we're going to think about obfuscation as theoreticians. We're going to talk about solutions kind of from a different type that are not just delaying the adversary. So here's my from practice to theory slide. So when we want to develop a theory of program obfuscation, there's some kind of standard questions that we need to answer. So first of all, we need to first we need to understand how to even define mathematically what does it mean for obfuscated code to be secure. Then we also need to understand how to construct such secure obfuscation and what are its applications. And when we answer these questions, our focus is going to be very different than that of practitioners. So for example, our definitions, they don't necessarily capture the way we use obfuscation in practice to do software protection. I think it's a really interesting question to try and define what does it mean for obfuscated code to protect a proprietary algorithm or to generate good polymorphic code. This is not really the type of things that we usually think about. Also in terms of constructions, so unlike practitioners, we don't care about manual obfuscation or semi-manual. So we are only interested in fully automated solution. So it's a compiler that takes as input a program and spits out an obfuscated program. We also want this compiler to be completely public, no security by obscurity. And as usual, we want some sort of provable security based on some acceptable hardness assumptions. In terms of applications, we'll be interested in different applications that come from complexity theory and theory of cryptography. So today we're going to talk about all these questions. It makes a lot of sense to talk about these questions in order, but instead we're going to be true to history. So in chronological order, the applications of obfuscation appeared very early, at least as early as Diffie and Hellman in '76. The first definitions were suggested around 2000, and only very recently we started making progress on constructions. So let's start by talking about some applications. So as you probably know, obfuscation is a very useful primitive. It has a lot of applications. My goal here is not to cover as many applications as possible. Instead, I just want to give you a flavor of what type of things we can do with obfuscation. Why do we see it as such a powerful primitive? And because we still didn't talk about formal security definitions, we didn't talk about what's possible and what's not possible, then for now, these will just be potential applications of obfuscations. Later, we're going to use these potential applications to motivate our formal security definitions. So we want definitions that are really strong enough to give us all these applications. OK, so let's get started. And we'll start with some very basic complexity theory. So in complexity theory, we classify different problems based on their computational hardness. And one type of problems that's been playing a central role in this theory are problems that have to do with understanding properties of computation. So here, the input to the problem is itself a program, and you want to learn some property of this program. For example, the halting problem, you need to determine if a given Turing machine halts or not. Satisfiability, you're given a circuit, and you ask whether there exists an input that will make the circuit output 1. So the reason that these problems are so interesting is that, first of all, they're hard. The halting problem is undecidable. Satisfiability is NP-complete. And secondly, these problems are kind of ubiquitous. So we see a lot of problems all over computer science and beyond that kind of encode inside them these problems about computation. So put together, we get these hardness results for a very versatile set of problems. OK, so this is classic stuff from the 60s and 70s. Now we want to take this a step forward. We want to go beyond NP-completeness. So if you look at the gap between P and NP, we see a lot of intermediate problems that are believed to be hard, but these problems also have some additional structure to them that makes them unlikely to be NP-complete. So one important example coming from game theory is the problem of computing a Nash equilibrium of a game. So this search problem is known to be complete for the complexity class P-pad. And another place where we see an abundance of these intermediate problems is in cryptography. And here we're usually also interested in understanding the average case hardness of these problems. So it turns out that many of these intermediate problems can also be described as problems about computation. But now we're no longer thinking about very general computations like in circuit satisfiability. Now we'll usually be thinking about computations that have some more structure. And our goal will be to prove that even such structured computation are still, in some sense, hard to understand. And turns out that obfuscation is kind of the perfect tool for the job. If you want to prove that a certain class of programs is hard to understand, then you can often look at obfuscated programs from this class, and these will be as hard as possible to understand. So to make this more concrete, let's see some examples. So let's go back to the problem of computing a Nash equilibrium of a game. So we believe that so Nash equilibrium is a really fundamental concept in the way we understand games and markets. And also this algorithmic problem of finding the equilibrium got a lot of traction. So today we don't know how to find an equilibrium efficiently. We believe that this is a hard problem. But we know that it's unlikely to be NP-hard. And we kind of don't really know what makes it hard. So for example, we don't know how to generate explicit games where finding an equilibrium could be hard. So the first step towards proving that Nash is hard was made in a sequence of work starting with Papadimitriou that showed that you can actually translate Nash into a problem about computation. So specifically, if you can find a Nash equilibrium of a game, you can also find fixed points in programs that have some specific structure. And a fixed point is just an input that the program maps back onto itself. The second step is to show that finding fixed points in such programs really is hard. And we can do this based on program obfuscation. So the idea is to design an obfuscated program that has the correct structure, but where the obfuscation somehow completely hides where the fixed point is. So if you want to know more about this hardness result, Nir Bitansky is going to be here next month, and he's going to talk about this. So So it's hardness for Nash, assuming specifically a notion called indistinguishability obfuscation.
What kind of hard? Or just that it's not in P?
So it's as hard as breaking indistinguishability obfuscation. So if indistinguishability obfuscation exists, so not in P, yeah, we don't expect it to be like NP hardness, but
Could be exponential hardness?
Yeah, it's sub-exponential hardness. So if you start with something with sub-exponential hardness, then you also get something with a different hardness, but still sub-exponential. So really today, the only way we know how to generate explicit hard instances for Nash is using program obfuscation and by going through this sequence of reductions. Okay. So this was an application from complexity theory. Now let me say a few words about how we use obfuscation in cryptography. So let's start with what's probably the most basic cryptographic application, secure communication. So Alice and Bob want to communicate privately in the presence of an adversary, Eve. And we can do this with symmetric encryption. So this is something that we understand very well. We know that one-way functions are necessary and sufficient for secure communication. But now we want to start thinking about more advanced applications. And here the picture becomes kind of much less clear. So in secure communication, the adversary Eve is kind of completely in the dark. But in more advanced application, we usually want to have some fine-grained control over what the adversary can and cannot learn, or what the adversary can and cannot do. So let's see some examples for this. So in public key encryption, for example, we want to give the adversary the ability to encrypt its own messages, but still the adversary should not be able to learn anything about Alice's messages. In fully homomorphic encryption, still the adversary cannot learn anything about Alice's messages, but now we explicitly want to give the adversary the power to change the message. So the adversary can compute any function homomorphically under the encryption. The last example is what's called functional encryption. So here we want to give the adversary some weak secret key that will allow the adversary to learn some specific function f of the encrypted message, but nothing else about the message. So for example, we can give the adversary a key that allows it to learn if the encrypted message is divisible by 7, but nothing else. So as you can see, by drawing this line between what the adversary can and cannot do, we can capture a lot of advanced applications. These are just examples from the domain of encryption, but actually this paradigm is much more general. So all of these applications are not known to follow based just on one-way functions. Usually, they're based on hardness of specific problems from number theory or from lattices. And also, going from these hard problems to the application is highly non-trivial. We have very complicated constructions and security reductions. So obfuscation suggests a very different way of doing things. Obfuscation gives us kind of a recipe for getting many advanced applications in a fairly straightforward way. And this includes even applications that we don't know how to get based on any other assumptions. So really the power of obfuscation in this context is that it gives us this fine-grained control over secrets. So going back to the example of secure communication, now you can take the secret key of this encryption scheme and you can put it inside an obfuscated program that will let the adversary do exactly what we want it to do, but nothing more. So for example, this program can let the adversary encrypt its own messages, or it can compute homomorphic operations on ciphertext, or it could leak some specific function of the plaintext. So again, obfuscation is considered as kind of a heavy hammer, but a lot of these applications you can even get based on probably weaker tools or assumptions. But what I find so appealing about obfuscation is its universality. It gives us a unified way of tackling many cryptographic problems. So questions about this? Okay, so just to sum up this part about applications, let me do a quick comparison between the way we used obfuscation in complexity theory and in cryptography. So in complexity, we started with some problem that we wanted to understand, in this case Nash. And actually the hardest part in this hardest result was to translate Nash into a problem about computation. But in the cryptographic applications, that wasn't really an issue, because in cryptography, we get to design the scheme, we get to design the problem such that we can really prove that it's hard. So we design our scheme to explicitly make use of obfuscated algorithms. Okay. So let's move on to talk about how we define security for obfuscation. So to understand what kind of security we need, let's start with an example application. So in the seminal paper from '76, where Diffie and Hellman invented public key cryptography, they also suggested to use obfuscation to transform a secret key encryption scheme into a public key one. So their suggestion was to take the encryption algorithm of this scheme together with the secret key hard-coded in it, and obfuscate this algorithm and publish it as the public key. So naturally, Diffie and Hellman did not specify a particular hardness notion of security for the obfuscation, but maybe we can try and guess what kind of security did they have in mind. So kind of reading between the lines of their paper, my guess is that their notion of security was probably derived directly from this application. So they wanted the obfuscation to be, in some sense, one way, so that given the obfuscated public key, it's hard to recover the secret key. And moreover, it should also be hard to do anything that compromises security of the symmetric encryption. So so we can definitely come up with some notion of security for obfuscation that gives us public encryption. But what about all of our other applications? So for every one of those applications, we can probably come up with some notion of security that makes it work. But that's not what we want. We want one notion that is kind of general enough to cover all of our applications. And this sounds like quite a challenge, because in every one of these applications, we want to obfuscate programs that have kind of different secrets. So we want the obfuscation to hide something completely different. So it could be a secret encryption scheme, but it could be something else altogether. So it took some time, but around 2000, Hada and later Barak et al. Had this very nice idea on how to define security for general purpose obfuscation. So this definition is called virtual black box, or VBB for short. So their idea is to require that the obfuscated program hides all the secrets of the original program. And a secret is just anything that you cannot learn by simply interacting with the program as a black box. So a bit more formally, the definition says that for every program P and for every property F of this program, if there's an efficient adversary that can learn this property from the obfuscated program, then this means that this property cannot be secret. So there's also an efficient simulator that can learn the same property given only Oracle access to the program, or black box access. So again, anything that you can learn from the obfuscated program, you could also learn given Oracle access. So questions about this definition? So what do we know about VBB obfuscation? So first of all, we know that there are some programs that are very easy to obfuscate, and we call these learnable programs. So a learnable program, a program is learnable if given black box access to the program, you can efficiently recover the entire description of the program. So for example, a program that just shifts the input by some constant, this program will be learnable. So intuitively, learnable programs don't contain any secrets. So you can kind of trivially obfuscate them. This obfuscation doesn't need to hide anything. So really, the interesting question is, what can we say about obfuscation for unlearnable programs? So let's see some example for such programs. We'll start with programs that are hard to learn, and we'll continue with examples of programs that are very hard to learn. So first example is pseudorandom functions. So an efficient algorithm that has black box access to one of these pseudorandom functions cannot distinguish it from a truly random function. So this function is clearly unlearnable. And really, we know that obfuscating PRFs and their variants is something that has a lot of applications. So pseudorandom functions are unlearnable in a computational sense. But we can also think about programs that are information theoretically unlearnable. So for example, you can consider, for example, point programs. So these are programs that output 1 on a single point in the domain and 0 everywhere else. So even if you have unbounded computational power, as long as you can't query this program on too many inputs, you cannot learn anything about the secret point. So for example, you can think about the point as being a password. And now this point program is just checking that you input the correct password. So if you obfuscate this program, then it shouldn't leak any information about your password. The last example that I want to mention is a sorting program that takes as input an array and sorts it. So the functionality of this program is completely defined. The only thing you don't know about this program is what kind of sorting algorithm it uses. So if this is something that you simply cannot learn given black box access, no matter how much computational power you have or how many queries you make. If I give you an obfuscation of this sorting program, you should not be able to learn what exactly is the algorithm that it uses. OK, so we have all these types of unlearnable programs. And intuitively, as you may have noticed, as the program becomes harder to learn, its obfuscations seem to become somewhat less useful. So back to our question, what can we say about obfuscation of unlearnable programs? So we need to start with some bad news here. So the same work that defined the notion of VBB obfuscation also showed that there are some programs that cannot be obfuscated in a very strong sense. So what they showed is a very contrived pseudorandom function, such that no matter how you try to obfuscate this pseudorandom function, you can always completely recover the key from the obfuscated program. So if you think about it, this example is kind of remarkable because in order to recover this key, you need to make some non-trivial use of the code of the program. You cannot just use it as a black box because then it will look random. You won't be able to learn anything. So even though these unobfuscatable programs are very contrived, still today we don't really know how to kind of separate them out. So any natural class of programs that contains pseudorandom functions also contains pseudorandom functions that are unobfuscatable. The only thing that we can say is that so far all of our examples come from this part of the diagram. So they're only unlearnable in a computational sense. So clearly, the existence of these unobfuscatable programs means that we cannot hope to get kind of a general positive result for a VBB obfuscation. So instead, what we do is we look at weaker notions of obfuscation. We look at relaxations of VBB. And intuitively, these relaxations are going to get around the impossibility result by only considering programs that are information theoretically unlearnable.
So for applications, are there applications that really need that part of the diagram?
This part?
Yeah.
For sure, yeah. I'm going to mention a couple of them in one slide. OK, so the way these relaxations work is as follows. We start with VBB obfuscation. Here, we wanted the simulator to be efficient. And in these relaxations, we're going to give the simulator more power. So this means that now the simulator can learn more about the program, which means that our obfuscation only needs to hide less. So by now, the most well-known relaxation of VBB is called indistinguishability obfuscation, or I/O for short. So this is what we get if we let the simulator be completely unbounded. So the simulator can make as many queries as it wants to the obfuscated program, to the oracle. It can learn all the functionality of this program. The only thing that the simulator cannot learn is if it cannot distinguish between two programs that have exactly the same functionality. So again, if we obfuscate one of these sorting programs that compute exactly the same function, and they also have the same size and the same running time, then given the obfuscation, you won't be able to tell which one of these programs being obfuscated. Regarding our other examples, so these examples can be obfuscated, but again, this obfuscation will be trivial. It doesn't give us any meaningful security because these programs are kind of trivially learnable by an unbounded simulator. OK, so if this notion of I/O seems kind of weak to you, then you're in good company. Even 10, yeah?
So again, just to repeat the definition of indistinguishability.
So there are two equivalent definitions. The first definition that I mentioned is to take VBB and let the simulator be unbounded. So anything that an adversary can learn from the obfuscated program, you should also be able to simulate using an unbounded simulator that can query the program everywhere it wants. So there's an alternative definition, which is more popular, I guess, which says that for every two programs that have the same size and the same functionality, obfuscations of these programs will be computationally indistinguishable from each other.
Computationally distinguishable for polynomial adversary?
Yeah.
And that's the same definition?
So the idea is that the unbounded simulator just defines what kind of information is hidden. So once you fix the fact that these programs have the same functionality, then the simulator cannot distinguish them, which means that they will be indistinguishable. So this is one direction. And in the other direction, if two programs are indistinguishable, you can always build a unbounded simulator that just maybe finds the minimal function that has this functionality and obfuscates it. So that's the two directions. OK, so it seems like the I/O definition is very weak. And even 10 years after it was defined, still people had no idea. People thought that it was completely useless. But it turns out that we just didn't know how to use it. So in the last 3 or 4 years, we made a lot of progress on applications of I/O. Today, we know that it has a lot of very strong applications. So really, the big success story of I/O comes from the fact that in this part of the diagram, we don't know of any unobfuscatable functions. But at the same time, we do have a lot of interesting functions that we do want to obfuscate. OK, so before we move on, I just want to mention another important definition of obfuscation that lies somewhere between VBB and I/O. So this definition is called virtual gray box obfuscation, or VGB for short. So here we again let the simulator be computationally unbounded, but we restrict the simulator to only making a polynomial number of queries to the program. So VGB is a stronger notion than I/O. It gives us meaningful security even for things like point programs that are unlearnable with a bounded number of queries. But still, VGB is not too strong. So just like I/O, we don't know of any impossibility results for VGB. As far as we know, it could be achievable for all programs. Okay. So just to conclude this part about definitions, let me give you kind of a very vague sense of the usefulness of these different definitions. So here's a very partial list of applications. Some of these are folklore. Some of these I just didn't include references. So in the interest of time, I'm not going to go over this, but I'll let you stare at this for a minute. And if you have questions on anything specific. So this list is still very dynamic. People are coming up with new applications all the time, or show that some of the existing applications could actually be achieved based on even weaker notions of security. So maybe taking an application that's only been known based on VBB and show that it's actually possible based on I/O. And actually, when we started this, then most applications were just only known based on VBB. So there are still some very interesting things that we simply don't know how to do based on I/O or VGB, but there are definitely some open questions here. So any questions about this? No, so it's not complete. It doesn't even represent the state of our knowledge, but even if I had like more room on the slide, then we're still working on this. So these are just the application of VBB, for example, that we don't know to be impossible. So we can do them based on VBB, but they could be just as impossible as VBB. So one thing you can do is try to get these applications out of the list by showing that they're simply impossible, or maybe get them down to one of the weaker notions. And sometimes you also show applications of I/O or VBB that you can do based on things that have nothing to do with obfuscation, maybe based on factoring, for example. This happens as well. OK, so for the rest of our time, we're going to talk about constructions of obfuscation.
I remember some results in the last couple of years about the programs that you can obfuscate, but you don't know if they're obfuscatable. So some way to obfuscate program assuming that they're obfuscatable or something.
So that would be a third definition for I/O. So if you have I/O, one way to think about it, so there's this very confusing name, very confusing security notion for I/O that's called best possible obfuscation. So what it says is that this is a type of obfuscation that if you use it on a program, this obfuscated program will hide anything. It will be as good as obfuscation as any other obfuscation of this program. So anything that you can hide about this program, this obfuscation will hide. And it's kind of easy to see that I/O satisfies this notion as well. So if there exists a good up to questions of size, maybe you need to pad the program before you obfuscate it. So why is that? So if there is, let's say, there exists a VBB obfuscation for my program, then it has the same functionality as my program, and I/O for my program also has the same functionality. So now you have two functionally equivalent programs. They will be indistinguishable. So you cannot learn more from the I/O obfuscation than you could from the VBB obfuscation. Okay, so this sounds like all you need in life is now I/O, but it's not it's not a very semantic definition. It doesn't tell you what you hide about the program. It tells you that anything you could hide, you do hide. So when I say that something is an application of VBB and not of I/O, I mean that in order to prove security for these applications, we need to use the semantics of VBB. But if VBB exists, you can just use I/O, and it will be good enough in terms of finding the actual obfuscated program. Okay. This is just part of the confusion that is different definitions of obfuscation. OK. So we'll talk about constructions of obfuscation. As you may know, in the last few years, there's been a lot of renewed interest in obfuscation. And this interest is coming from these breakthroughs we have in terms of constructions. So these breakthroughs that we had on constructing obfuscation didn't come out of thin air. So here are some important milestones along the way. So in 2002, Bonnet and Silverberg suggest a notion they called cryptographic multilinear maps. This notion extended an existing notion called bilinear maps. And they also showed that these maps, if they exist, they will have far-reaching consequences in cryptography. In 2013, Garg, Gentry, and Halevi suggested a plausible lattice-based construction that gives us a very good approximation of these multilinear maps. Shortly after, Garg et al. Gave a candidate construction of general-purpose obfuscation that is based on these multilinear maps. And since then, many, many other constructions were suggested, and all of these constructions are based in one way or another on multilinear maps. So the existence of all of these constructions definitely raises our confidence in the existence of obfuscation. So if you ask a cryptographer whether they believe that general-purpose obfuscation is possible, then before 2013, the answer would most definitely be no. After 2013, it really depends on who you ask and probably also on the day of the week. So these constructions, they give us some confidence, but not as much as we would have liked. I think that getting this confidence up is probably the most important question in this field today. So next I'm going to talk about this confidence we have in our construction. Where is it coming from? So in the short time we had, we made a lot of progress on this. So we went through kind of several different generations of constructions and security reductions that became increasingly more convincing. So next I want to kind of take you through these different generations. Okay, so when the first candidate construction was suggested, our main reason to trust in its security was that we didn't know of any explicit attacks. So if you are an optimist, at this point you can hope that this construction gives you the best possible security. So unobfuscatable programs remain unobfuscatable no matter what construction you use. But for everything else, you can even hope that this construction gives you VBB security. So of course, this type of argument is highly unsatisfying. And really, because it could change at any moment, right? And really, since this construction was suggested, there's been a lot of movement on understanding the security of this construction. So it was broken, and it was fixed, and it was broken again, and fixed again. But after all this movement, I think that today the bottom line kind of remains almost the same. So if you instantiate this construction with the right construction of multilinear maps, and you introduce some safeguards to your obfuscation construction, you can resist all known attacks. So this is our starting point. So from now on, we're going to ask for more. We want to get some provable security. And today we're going to focus on reducing.
So there's no real proof. There's just a reduction to another problem. There's no.
So in generation 0, there's nothing. There's just these no attacks.
So there's no proof of security.
So this is just generation 0. We're going to get much better from here. So this was the state of affairs like in the week after, and also like this is still going on. But there's also some parallel efforts of I'll show you. So today we're going to focus on getting some provable security for these constructions. So we'll focus on reducing the security of the obfuscation to the security of the multilinear maps. Now,
I'm sorry, can you say what a construction is? Is it given some program you can
so a construction
program that has the same output?
Yeah, so a construction of obfuscation is a compiler that takes programs and spits out obfuscated programs.
Not circuits, just Turing.
So okay, so you can represent the programs. So it's a good question how you represent the program. So the simplest answer is that it doesn't matter. Let's say that you have obfuscation for circuits, then you take your program that is written in C, you translate it into a circuit, and you obfuscate it. So that's true, but there's also a question of kind of efficiency. So, for example, if you can obfuscate Turing machines in contrast to obfuscate circuits, then when you obfuscate Turing machines, you want that the size of this obfuscation doesn't grow with the running time. This is something that you can ask. So this will be harder to do than to obfuscate circuits. Okay. The construction that we'll talk about today are for circuits, but actually we have results that for certain notions, like indistinguishability obfuscation, you can go from obfuscation of circuits to obfuscation of Turing machines up to some asterisks, but generally that's true. Okay, so I'm going to focus today on reducing the security of the obfuscation to that of the multilinear maps. There's also a lot of work on understanding security of candidate multilinear map constructions. but I'm not going to talk about that too much today. If you want, you can ask me, and I'll say a little more. Okay. So let's start with a very quick overview of what are multilinear maps and how do we use them to construct obfuscation. So a multilinear map is an encoding scheme that allows you to encode elements taken from some ring or a field. And what you can do with these encodings is you can homomorphically evaluate arithmetic circuits on them and test whether the circuits vanish or not, so if they evaluate to 0 or not. So you can't really test every circuit. The only circuits you can test are multilinear circuits, so the degree in each input variable should be 1. So the actual circuits that are supported, their structure is a little more complicated, but for now you can think about them as multilinear. Later we're going to go into the details a bit more. So importantly, these encodings should also give you some security. They should be hard to invert. And ideally, what we want is that these encodings don't let you learn anything about alpha 1 through alpha n, except for what you can anyway learn using these homomorphic operations in zero test. So for example, you can always test if alpha 1 is equal to alpha 2. You just subtract them and you check if you get 0. But testing if alpha 1 is equal to alpha 2 square, this should be hard, because this is something that you can't do with a multilinear circuit.
So think of all these alphas living in some large field?
Yeah, exactly. OK, so we have these multilinear maps. So how do we use them to construct obfuscation? So many of the obfuscation constructions, at least the earlier ones, had the following extremely simple structure. So your obfuscator takes as input a program, and it translates it into a list of field elements. And then you encode these elements with a multilinear map. And this is basically your obfuscated program. And to evaluate this program on some input x, what you need to do is to homomorphically evaluate over these encodings some multilinear arithmetic circuit that depends on x. And if the circuit vanishes, you say that the program outputs 1. Otherwise, the program outputs 0. So you can naturally extend this to programs that have more than one input bit. OK, so back to our reduction. The next step will be to specify what notion of security do you want for the obfuscation, and what kind of security do you need from the multilinear maps. So in the different generations, we're going to consider kind of different combinations of these notions. So in the first generation, we give a reduction that considers the strongest possible security for both the obfuscation and the multilinear maps. So we get VBB obfuscation based on what's called generic multilinear maps. So let me tell you what these are. So in generic multilinear maps, the actual encodings are replaced with this black box. And the way to use this black box is you use it exactly like you would use the encodings. You query the box with some multilinear arithmetic circuit, and the box tells you whether the circuit vanishes on the encodings or not. So you can actually think about this box as kind of an abstract way of capturing multilinear maps that have perfect security. So right now, the way you should think about this reduction is giving us kind of a transformation between ideal black boxes. So if you give me a black box that evaluates multilinear maps, I can use this box to build another box that evaluates an arbitrary program, and this transformation kind of preserve security. OK, so at first glance, when you think about this reduction, it's not completely clear what kind of confidence are we supposed to get from this. Because we know that VBB obfuscation is not possible in general. And this means that generic multilinear maps are also impossible to realize in the plane model.
Like a random oracle model kind of result?
So this is kind of a random oracle result that we take. Like, there's a lot of results in cryptography where you want to build something from a hash function, but you can't really prove that it's secure. Or maybe you can prove that you cannot prove that it's secure. And to get around this, you kind of replace the hash function with a random oracle, with a function that doesn't have an actual representation. It's an oracle. And then you can get around a lot of impossibility results. So this is a similar type of, and this is kind of a heuristic. If you can break this, then you can kind of maybe we don't expect you will be able to break the construction with an actual hash function. Or maybe if you can break it, you can say something interesting about a hash function like SHA. You can say that in some sense it doesn't behave like a random oracle. So this is kind of the similar methodology, except that instead of a random oracle that doesn't have any algebraic structure, we think about an oracle that implements this kind of group or field with some limited algebra. But again, the security comes from the fact that it's an oracle. So I'm going to suggest a couple of different interpretations for this reduction. So first of all, this reduction already means that any attack on this obfuscation scheme has to be non-generic. So it has to use the actual representation of the multilinear maps. It can't just use the multilinear maps as a black box. So for example, you can think about a non-generic attack that exploits some flaw in a specific multilinear map construction. Another example is that if you try to obfuscate the unobfuscatable programs of Barak et al., then their attack is also non-generic. So it works for every multilinear map, but it needs to know it really needs to know how these multilinear maps are implemented. So it doesn't relativize. It doesn't work if the multilinear maps are just black boxes. So these are attacks, as I mentioned before, that are kind of remarkable. We don't have any example for another non-generic attack that works for every multilinear maps. This is something special. OK, so the second interpretation I want to offer is that this reduction gives us some sort of a connection between the security of the obfuscation and the security of the multilinear maps. And this connection goes well beyond generic security. So what we actually want is to connect between weaker notions of security that are not already known to be impossible. And as we'll see, this generic reduction plays a central role here as well. OK, so following this interpretation, in the second generation, we're going to aim at getting indistinguishability obfuscation rather than VBB. And the big question is, what kind of security do we need from the multilinear map? So it turns out that coming up with any plausible notion of security that gives us I/O, even a very strong notion, is already a non-trivial task. So Paneth et al. Suggested such a notion, and today we'll call this Über secure multilinear maps. So let me tell you about that. So unlike in generic security, in Über security, the encodings are not black boxes. They have actual digital representation. But again, we want that if we have a pair of distributions over sets of encodings, the only way to distinguish these two sets is using the valid legal operations on the encodings. So if you imagine a generic versions of these encodings, if you cannot distinguish between the generic version, then the encodings themselves should also be indistinguishable. So this is kind of the intuition. It turns out that you need to be really careful in how you define indistinguishability between these black boxes. So Paneth et al. Observed that the right definition is indistinguishability by an unbounded distinguisher that can only make a polynomial number of queries to these boxes. So if you require that the distinguisher is bounded, then this definition becomes way too strong. It can actually, you can show that it implies full-fledged VBB obfuscation, so it's impossible. If you let the distinguisher unbound a number of queries to these boxes, then we can show that it can always recover what's inside the box. And then this definition becomes kind of trivial. It doesn't give you anything. OK, so as the name suggests, Über security is considered this very strong notion. Also, we say that the exact formulation is kind of delicate. So let me try and give you a more convincing argument for why Über security is really the right notion to look at. So in generation 2.5, we give kind of a full characterization of the relation between Über secure multilinear maps and obfuscation. So we showed that from Über security, you can get not just I/O, but also the stronger notion of VBB obfuscation. And we also showed that Über security is necessary to get VGB. So if you have VGB obfuscation, you can use it to construct Über secure multilinear maps. So this equivalence is not perfect. There's some details missing here, which I'm not going to get into. But I'll just say that still this result gives us a good characterization of the exact power of Über security with relation to obfuscation. Okay, so before we move on to the next and final generation, I just want to give you an example for how to use Uber security, so we can see how all these ideas kind of fit together. So I'll show you how to get from Uber security to I/O. This proof is extremely simple. If you want to go all the way to VGB, then the proof becomes much more involved. So to show I/O, we start with a pair of programs that have exactly the same functionality. And we want to show that their obfuscations are indistinguishable. So the first thing we do is we use Uber security. These two obfuscated programs are just two sets or two distributions over encodings. So we can only distinguish them if we can distinguish their generic versions. And now that we have generic encodings, we can use our generic reduction. We can use the fact that this obfuscation is now VBB secure. So it's equivalent to just having a black box that contains the original program. And since the original programs are functionally equivalent, then you cannot distinguish these black boxes. Questions about this? Okay, so the third and final generation already includes kind of a lot of work. It's probably still in progress, so let me just tell you what is the state of the art here. So today we know how to base indistinguishability obfuscation on multilinear maps that support degree 5. So you only need to multiply 5 encodings at a time. And these encodings should satisfy relatively mild hardness assumptions called DDH, decisional Diffie-Hellman. Yeah.
This is basically like multilinear degree 5 polynomial?
Yeah, so you can have, exactly, you can have many encodings, but the kind of the set of polynomials you can evaluate on them is, let's say, multilinear of degree 5. Okay. So as you can see, there are kind of two dramatic improvements here. First of all, the degree of the multilinear map is a small constant. It doesn't grow with the size of the program. So this is definitely an advantage in terms of efficiency, but it also gives us a lot in terms of confidence. So today, our candidate constructions of multilinear maps, they do support unbounded polynomial degree. But the hope is that maybe we can get a better understanding of these constructions and their security if we restrict ourselves to only looking at degree 5. Or maybe in the future we can get much better construction of 5 linear maps directly. The second improvement is again the assumption DDH. I'm not going to say too much about this assumption. I'll just say that it follows from generic or Uber security. And we actually believe that this is a much weaker assumption. It's also much kind of cleaner to state. It's one of the most basic hardness assumptions that you can even write down in the context of multilinear maps. Yeah?
So is there anything special about linear? Can you have multi-quadratic? Or like, why is it linear? Why is it so important?
You can also, so the answer is there's nothing special about linear. These constructions also give you kind of bounded degree. Linear is enough for obfuscation. So the multilinear thing is just a simplification. Actually, these things have kind of a more subtle asymmetric structure. So when we talk in the second part of the talk, we're going to talk about construction, and we'll see exactly the interface of the multilinear maps. And if I'll remember, or if you remind me, then I'll say kind of what kind of variants you can think about. Okay, so and I can also, then I will also be able to kind of say what the DDH assumption means, even though we're not going to need it for the rest of the talk. But if you're curious, then we still don't have the exact machinery, but we will. Okay, so this construction is kind of remarkable. And if you want to know more about it, then again, as I mentioned before, Nir Bitansky is going to be here next month, and he promised to tell you about this construction as well. I hope that by then it will already be like 4 linear or 3 linear maps. So one interesting thing about this construction is that it doesn't follow the blueprint that we've described so far. In fact, it makes the construction makes non-black box use of the underlying multilinear maps. So when you execute the obfuscated program, the program itself generates more encodings. So it really depends on the exact and how encodings are represented. So it turns out that this non-black box use of multilinear map is somewhat inherent. We know that if you had a black box construction of I/O based on any constant degree multilinear maps, then you could kind of generically get rid of these multilinear maps and replace them just with the minimal assumption that one-way functions exist. So getting I/O from one-way functions would be really amazing, but it's probably kind of too good to be true. So the common way to interpret this result is as giving us a barrier on the power of black box construction based on constant degree multilinear maps. So now we have this interesting separation between the power of black box and non-black box construction based on this primitive. Okay, so let's, to conclude the entire first part of the talk, let me summarize what we know about constructions and what do we know about the connection between obfuscation and multilinear maps. So to get VBB security, we need to assume that the maps are generic or perfect. So unless our encodings are in some sort of a black box, then we run into all of the impossibility results. VGB is already a definition that we can possibly get in the plain model based on the strong notion of Über security. And I/O is something that we can already get based on much weaker notions, specifically DDH on degree 5 maps. And unlike VBB and VGB, here we don't have any implication in the other direction. And really, we continue to look for constructions of I/O that can be based on even weaker assumptions. OK. Good. So in the second part of the talk, I'm going to tell you more about this first connection. So I'm going to show you exactly how to construct obfuscation based on multilinear maps. And I'll give a generic proof of security. So this construction is very simple. But at the same time, I think that the security proof is giving a lot of insight into what is going on. And also, as I mentioned before, this construction is kind of the starting point for all of the black box construction that followed it. So without further ado, let's...
That's a good point to do a 5-minute break.
Yeah, sure. Perfect.
Okay, so let's resume at 11:37.
Yep. everyone here. So okay, so now we're going to take a look at a construction. And let me just remind you what do we want to construct. So we want to construct a compiler that takes as input a program, translate it into a bunch of encodings in a way that you can really learn the output of this program on any input of your choice by simply homomorphically evaluating some valid arithmetic circuit over these encodings and learning if it vanishes. And in terms of security, we want that if someone gives you these encodings inside a black box, then this should be equivalent to a black box that evaluates the original program. So you should be able to simulate one box using the other. OK, so our construction is following this very powerful idea called bootstrapping. So bootstrapping gives us it's giving us this blueprint for how to construct general purpose obfuscation. So this blueprint says that if you want to obfuscate arbitrary programs, first you only need to obfuscate circuits in NC1, and then you can bootstrap this obfuscator and get obfuscation for all programs based on the hardness of the learning with errors problem. So specifically, what we need for bootstrapping is fully homomorphic encryption that has the property that decryption can be executed in NC1. And we can get this based on the hardness of LWE. So I'm not going to describe the bootstrapping step in details. I'll just give you the very high-level idea. So here, to obfuscate a program, you just encrypt it with a fully homomorphic encryption. So this gives us very good security. It completely hides the program. But it's still not a good obfuscation, because now you can't evaluate this program. What you can do with this encryption is you can homomorphically evaluate, because it's fully homomorphic, you can homomorphically evaluate it on some input. And what you get is the output of the program still under the encryption. And now, to get this output in the clear, I'm also going to give you an obfuscated NC1 circuit that allows you to decrypt this value. So there's a lot of missing details here. So for example, I need to show that the obfuscated decryption circuit doesn't break the security of this obfuscation. But I'm not going to go into more details. So following this idea, all we need to do now is construct obfuscation for NC1 circuits. And in order to do that, we're going to exploit the fact that these circuits can be represented as polynomial time branching programs. So let's start with a quick reminder of what branching programs are. So a branching program all the matrices are back. OK. Right? There were some matrices missing on the right, right? I wasn't imagining it. Never mind. So a branching program consists of a bunch of permutations. And we're going to represent these permutations as just square 0, 1 matrices. So here we have a branching program that has 12 levels. And in every level, we have two matrices, M0 and M1. Now, this program also has an input. And every level of the branching program is associated with one of the bits of the input. So here, we denote this with colors. So all the blue levels are associated with X1. So from now, our slides are going to become much more colorful. So to evaluate this program on some specific inputs, let's say 0, 1, 1, 0, you first need to select one matrix in every level based on the input. So in the blue levels, they're associated with X1, which is 0, so you take the 0 matrices. The green levels are associated with X2, which is 1, so you take the 1 matrix. So once you selected one matrix in every level, you multiply together all these matrices. And the branching program is designed in such a way that the product will always be one of two special matrices called top and bottom. So if the program accepts, the product will be top, otherwise it will be bottom. OK, so now we want to obfuscate this branching program. And the high-level idea is that we want to kind of hide the matrices of this program as much as possible, but without destroying the functionality of the program. So we're going to do this in 2 easy steps. The first is to randomize these matrices. and then we'll encode these matrices entry by entry using a multilinear map. Okay, so the randomization step is following this really nice idea of Killian. So we'll take the matrices of our branching program, and between every two levels, we're going to place a random regular matrix Ri together with its inverse.
So these matrices are of constant size, right? Like 5?
They could be of constant size, but actually for this construction, they could be arbitrary polynomial size. So for NC1, you just need constant size, but we're not going to use this in the construction. The number of matrices, though, is not constant. Okay, so these R matrices are not going to be 0, 1. They're going to be over some large field. So now you multiply every matrix of the branching program with the random matrix on the right and with the random inverse on the left. And we denote these randomized matrices by m tildes. So the first thing to notice is that this randomization does not change the functionality of the program. So when you evaluate, you take you multiply one matrix in every level, and now all the random matrices and their inverses are going to cancel each other out, and you're going to be left with exactly the same product. So for example, here, if the program accepts this input, then the product of all these matrices will be top. But now the key property that we're going to use is that if you look at the distribution of these highlighted matrices, these matrices look completely random, conditioned on the fact that their product is really top, right? Okay, so intuitively, this means that from these matrices alone, you can't learn anything except for the fact that this program is accepting this particular input. Now, you could maybe, at this point, maybe guess that maybe just randomizing the branching program is already giving you a good obfuscation. But it turns out that that's really not the case. So if you look at the distribution of all the matrices together, not just the highlighted one, then because we use the same Ri matrices to multiply the top row and the bottom row, then you can kind of exploit this to completely recover the original matrices of the branching program. So just the randomization step on its own is not going to give you any security. So we're not going to stop here. The next step will be to encode these matrices using a multilinear map. So I already told you what multilinear maps look like, but now we'll need to get a little more specific. So again, a multilinear map lets you encode an element alpha from some large field. And this encoding will be with respect to some control set S, which is just a subset of a universe U. So intuitively, this control set is going to help you keep track of what kind of operations you can perform over this encoding. So when you have a bunch of encodings, you can compute homomorphic. You can homomorphically evaluate valid arithmetic circuits. And valid arithmetic circuits are compiled of the following permitted operations. So the permitted operations are as follows. You can take two encodings under the same control set, and you can add them together or subtract them. And the result will be an encoding of the sum or the difference under the same set. You can also take two encodings under disjoint sets, and you can multiply them together. The result will be an encoding of the product under the union of the two sets. So intuitively here, the requirement that the two sets you start with are disjoint is what captures the fact that the circuit is going to be multilinear. You can never take an encoding and multiply it with itself. The last operation you can do is if you manage to get an encoding under the universe set, under the maximal control set, then you can test and see if this is an encoding of 0 or not. So again, we're going to assume that our encodings have a generic security. So the only thing you can do with them is evaluate circuits that have this structure. OK, so now we take our randomized matrices and we're going to encode them with the multilinear map. So our universe set is going to contain all the integers from 1 to 12. And in the level I, we're going to encode both matrices, entry by entry, under the control set that contains a single integer I. So now the obfuscation simply consists of all of these encodings. So to evaluate this obfuscated program on some input, you first need to homomorphically multiply all the matrices that correspond to your input. And you can really do that because this is a multilinear operation, and all these matrices are in different levels. They are encoded under disjoint sets. So after you multiply all these matrices, all the random field elements are going to cancel out. And what you get is an encoding of a 0-1 matrix, either top or bottom, under the universe set. So now what you can do is just zero test one entry where these two matrices differ, and you learn if this program accepts or rejects. OK, so this is the basic construction. It's oversimplified. In order to prove security, we're going to need to change this construction some more. But let's go ahead and start with the security proof, and we'll introduce changes as we go along. So in the security proof, we have all these matrices inside a black box. We also have an adversary that can query this box with a valid arithmetic circuit, C, and learn if it vanishes or not. And this adversary, based on these queries, can just output some bit B that it learned about the program. So now what we want to prove is that there's also an efficient simulator that can learn the same bit B given only Oracle access to the program. So the simulator is going to work by internally emulating the adversary in its belly. And whenever the adversary makes a query, the simulator needs to answer this query. But now the simulator has no idea what is supposed to be encoded inside this box, because these encodings depend on the matrices of the branching program. But the simulator only has Oracle access to the program. It has no idea how it's implemented. So instead, our strategy will be to take a close look at this query circuit C and try to understand whether it's supposed to vanish on the encodings without even knowing what the encodings are. So for example, if the circuit C happens to correspond to an honest evaluation of the obfuscated program on some input X, then we can just query our program on an input X, and based on the output of the program, we can decide if this query is supposed to vanish or not. Now, of course, the adversary doesn't have to query something that corresponds to an honest evaluation. It could query any valid circuit. But the heart of the security proof is to show that this doesn't really help the adversary. So even if the adversary makes a query that is dishonest, we can still answer these queries. So in the rest of the security proof, we're going to go over the different type of queries that the adversary makes, and we'll show that we can always answer them correctly. We'll start with very simple queries, and we'll kind of work our way up. So the first type of queries we'll consider are what we call single input queries. So in a single input query, it's a query that only depends on the entries of matrices that correspond to some specific input. So it could be an honest evaluation. The query could be multiplying all these matrices together. Or it could be an arbitrary query that only depends on these entries. So now, again, because of the randomization that we did, we know that the distribution of these matrices is completely random, conditioned on their product being correct. So what we can do is just query our program on the corresponding input, learn what the product of these matrices should be, and then we just sample random matrices that have the correct product. So now we're going to evaluate the query over these random matrices that have the same distribution. And if this query vanishes, and we see if this query vanishes or not, and based on that, we answer the query. So again, this case is basically telling us that from these matrices, you can't learn anything except from this particular output. Our next case is what we call mixed input queries. So a mixed input query is just the sum of a few single input queries. And here I just drew the beginning of the branching program to save space on the slide. So now the naive way to answer this query is to independently simulate every part of this query as if it was a single input query. So we learn if every part vanishes or not. So if all the parts evaluate to 0, then their sum is also going to be 0. But if both of the parts evaluate to non-zero, it doesn't mean that their sum is going to be non-zero. It could be that these two parts somehow cancel each other out. So remember that in the real obfuscation, if you look at the distribution of the matrices in every part, then it looks random. But these two distributions are correlated. So they use the same random matrices, the same random Ri matrices. So this correlation can cause the sum to vanish. But during the simulation, we can't really account for these correlations because we don't know the original matrices. We only know the products. So the only thing we can do is sample independent random matrices in every part. So we completely lose track of the correlations. We don't know if the sum is supposed to vanish or not. So I told you we're going to run into some troubles. So now we need to change the construction a little bit. And we're going to change it by introducing some more randomization. So now we take the matrices of the branching program that's already been randomized once. And we're going to multiply every matrix with a random non-zero scalar, alpha, from the field. So unlike before, we don't use the same randomness for the top row and the bottom row. We multiply the M0 and the M1 matrices with different scalars. So first thing to see is that even this extra randomization still doesn't change the functionality of our program. So when we evaluate the program, we multiply one matrix in every level. And because this is a multilinear operation, then the product of the matrices will just be multiplied by some product of the alphas. And since all the alphas are non-zero, then the result of our zero test is not going to change. OK, so now now back to our mixed input query. Let's see what we've gained from this. So now both parts of the query correspond to different inputs. So both of these parts are going to get multiplied by some product of alphas.
Finds an entry in which one, like t equals 0 and b.
Yeah, so you test some specific entry. You know that you're looking for an entry where top and bottom.
Different. Now you want one to be 0 and one non-zero, right?
So the zero test, anyone tells you if it's 0 or non-zero. And since these are 0, 1 matrices, originally there were 0, 1 matrices, then one of them is going to be 0 and one of them non-zero. And since we multiply by some non-zero scalar, then that's going to be the case even after. OK, so every part of this query is going to get multiplied by a product of alphas. But because they correspond to different inputs, at least one of these alpha coefficients is going to be different. So even if both parts of the queries evaluate to non-zero, now it's very unlikely that these two parts are going to cancel each other out. So intuitively, what we're doing here is we're using these alpha coefficients to break any dependencies between different single input queries that we don't know how to simulate. Good. So we know how to answer single input and mixed input queries. The next type of queries we'll consider are what we call inconsistent queries. So here's an inconsistent query. It looks a lot like a single input query, but it's not. Can someone tell me why, maybe? What's the problem with this query? Why is this not a single input query? So it's not a single input query because so it touches one matrix in every entry, but we see that both levels M1 and M5 are blue, but still this query is touching matrices that are inconsistent. So our randomization still tells us that if you look at these matrices, they look random, conditioned on their product. But actually, because these matrices don't correspond to an honest evaluation of the branching program on any specific input, we simply have no idea what the product should be. So this is a problem. Again, we're going to have to change our construction. But this time, we're going to change the way we encode things. So specifically, we're going to change our control sets. And we're going to design our control sets in such a way that all the valid queries now cannot be inconsistent, can never be inconsistent. So let's see how it works. So originally, we encoded every matrix under the control set that contains a single integer, I. Now we're going to add to our universe a copy of all of these integers. And we'll encode every matrix under a set that contains two integers, I and I hat. Now if you focus for a second only on the blue levels, then we're going to keep the sets for the 0 matrices on top unchanged. But for the 1 matrices on the bottom, we're going to kind of rotate these hats around. So if you stare at this for a second, you can see that now the only way to collect all of these integers is by combining together either the matrices on the top or the matrices on the bottom, but you cannot do it by kind of mixing the two. So we call this a system of sets a straddling set system. And the best way to think about a straddling set system is to think about the sets as being these puzzle pieces that can only be combined in specific ways. So if you want to add two pieces together, they need to have the same shape. If you want to multiply two pieces together, then their shapes kind of have to fit together. And if you want to zero test something, then you have to first complete the entire puzzle. You have to reach the universe set. So now, as you can see from this picture, the pieces on the top can only be combined with each other, and same from the bottom. Okay, so from now on, all the proofs are going to be by picture. OK, so now we're going to take a separate copy, a disjoint copy of the straddling set system for every one of the colors in our branching program. And what we get is that between levels that have the same color, you have to use consistent matrices. But between different colors, there are no constraints. So this is something that is important for the functionality. We should still be able to evaluate this program on an arbitrary input. OK, so now that our set system tells us that we don't have to worry about inconsistent queries, so now I'm claiming that we're almost done. So any query, take any query over these entries. You can view this query. This query is computing some polynomial in the entries of these matrices. You can think about this polynomial as a sum of monomials. And because of the way we chose our set system, every one of these monomials is going to be consistent with some input. So now the sum of the monomials is just a mixed input query. This is something that we already know how to answer. So does someone see the flaw in this argument? There's something missing here. So the problem is that we didn't really think about efficiency. So even if our query can be represented by a small valid arithmetic circuit, it could still be that this query consists of an exponential number of monomials, where every one of these monomials corresponds to a completely different input. So to simulate this query, we'll need to simulate every one of these monomials separately, and we'll need to query the program on every one of these inputs. So our simulation becomes completely inefficient. So by the way, if you just want to prove that this construction gives you I/O security, then you're already done. We already have inefficient simulation. But if you want to go all the way to VBB security, we first need to get to deal with these inefficient queries. So this will be our fourth and last case. So here is an example for a specific inefficient query. So this query is taking all the blue matrices that correspond to 0 and multiplies them together, same with the matrices that correspond to 1. And now, since these two pieces have the same shape, we can add them together. We can do this for every one of our colors, and then we can multiply all these products together. So if you open up the parentheses here, you see that this query consists of an exponential number of monomials, one for every possible input. Okay. So this is the type of queries that we're worried about. Now, just to note that this specific query is maybe not so problematic, because as you can see in this query, we multiply things kind of completely out of order. First, all the blue matrices, then all the green matrices. And this means that all of our random matrices, the Ri matrices, are not going to cancel each other out. So this expression will almost never evaluate to 0 over the randomness of the obfuscation. So we can safely answer that this evaluates to non-zero without even thinking about it. The problem is that we don't really know if this is always the case or not. So in every inefficient query that we can think about, the random matrices don't seem to cancel each other out. But we don't know that if this is the case in general. So if you think about it, what we're trying to prove is some kind of a circuit lower bound for this model of computation of valid arithmetic circuit. We want to show that a complicated function, a function that depends on many inputs, requires a large valid arithmetic circuit, let's say at least as large, let's say linear in the number of inputs. So we tried to prove this lower bound. We didn't succeed. So what we did instead in high level is to again change the construction, change the control set such that the set of valid arithmetic circuits becomes so restricted that we can actually prove the lower bounds that we need. So let me show you how this works. So we're going to change the construction to use something that we call dual input branching programs. So in a dual input branching program, you take the levels of the branching program and you kind of rearrange them, and you divide them into pairs, such that every pair of colors will appear at least once in this program. So now, for every pair of levels, instead of giving out two matrices in every level, you're going to give out all the possible products of these matrices. So basically what you're doing here is you're taking two levels with two matrices each, and you're turning them into one big level with four matrices. So pictorially, it's as if you took the puzzle pieces and you kind of glued them together. So now you can't use just one piece, you have to use two pieces at a time. So now you have this new branching program where in every level you need to select one of four matrices by looking at 2 bits of the input. So this is why we call this a dual input branching program. So now, if we go back to our inefficient query, if you try to add together all the matrices that correspond to 0 and all the matrices that correspond to 1, you have to, along the way, also collect at least one piece from every other color. And this will already fix all the other bits of your input. So now you can only multiply this expression with things that are consistent with one particular input. So this completely kills the attack that we've seen before. And more generally, we can prove this lower bound that I mentioned. So if you have a valid query of size x, you can always efficiently decompose this query to a sum of at most x single input queries. So this is the lower bound that we need to prove that the simulation is efficient. And this concludes the proof of VBB security. Thank you. Questions, please.
So which of these parts seem to be like essential? So if you wanted to get rid of multilinear maps, for example, so where would I presume some parts don't really need them.
OK, so obviously they're not necessary. You could hope to get obfuscation based on things that look completely different. Maybe bilinear maps, maybe lattices, maybe, I don't know, basic number theory. I don't know. One thing to note is that once your security becomes strong enough, so if you only get I/O, then sure. But if VBB or VGB exists, then you can actually use this obfuscation to construct this algebraic structure of multilinear maps. So far, we had really no success in constructing maybe 2 linear maps from 1 linear map, or 3 linear maps from 2 linear maps. This is something that we don't know how to do. So if you manage to construct obfuscation from something completely different, then you get this cool result that you can take some group with some structure with cryptographic hardness to it and kind of upgrade your algebraic structure without compromising the hardness. So this will be kind of cool. Other than that, we can't say anything that has the word inherent in it. So the only thing we can say is that this is stronger than multilinear maps. So again, this construction uses many levels. So kind of the cardinality of the universe set grows with the program. As I mentioned, we now know how to get I/O based on just multilinear maps that support 5 multiplication at a time. So your universe set is just 1 to 5. You have a lot of encodings. And really, the construction looks completely different. You can't express it in this black box model. It's this recursive construction where you have obfuscated programs that generate larger, obfuscated programs that generate larger. And this is kind of based on a few cool ideas that have to do with the connection between obfuscation and functional encryption. That's it. Hope it answers.
So you said before that VBB doesn't exist, right? So
yeah.
What do you mean by if we have VBB, or what
So right, in a certain model, you can talk about VBB, like in this model or in others. But in order to build multilinear maps, you just need VBB for a specific function. So no, but you're right. I mean, you cannot hope to get. You can't really use VBB to construct multilinear maps that are generic. That's not possible, right? Because multilinear maps are kind of complete. You can use them to get obfuscation for anything else. So you can't hope to get like VBB for a specific function that gives you multilinear map. This function is also impossible to obfuscate. And the proof goes through this elaborate construction of branching programs. So you kind of get an impossibility of VBB for a very specific natural algebraic function. And this impossibility goes through like showing that this function is kind of complete in this weird way.
This whole theory of applications of VBB and all this list of things that.
Yeah, so I think it's still meaningful because for most of these applications, we don't have an impossibility result for the application. So it's very likely that for this so it could be that for the particular function that you want to obfuscate in this application, we don't have impossibilities. So again, some functions are complete. You can use them to obfuscate everything. And these functions are impossible. But some functions could be that VBB is possible for them, and we don't know how to separate one from the other. So we don't know how to look at a function and say this function is possible, impossible. So the natural thing to say is to say, I don't want to think about VBB for anything. But as we can see, there are certain things that I/O is just not good enough for. So you can say, I can't get this from obfuscation. But again, plausibly, our constructions already give you this. Another example is that in the security proof, there are certain applications that you can get both from I/O and from VBB. From VBB, it's like one line. And from I/O, you have to do like an extremely complicated construction and analysis. And for this specific function, you don't have any reason to believe that it's not VBB obfuscatable. So the question is whether all of this complication is necessary in some sense. So it's necessary for our confidence. Until we get a better understanding of what's possible to VBB obfuscate and what's not, then it's definitely necessary. But it's still useful to understand like what happens in a world where we have VBB for what we can hope to get VBB for.
Questions?
Thanks.
We're staying until when?
Until Wednesday afternoon.